So now I'll start recording. People tuning in the future, the one thing that we talked about that I haven't mentioned on here is that I'm going to have homework now due on Monday nights, which gives you an extra day to work on it so that it's not due on Sunday nights when everything else is due for other classes. So just so you know, homework will now be due on Monday nights. And then I also mentioned that the review for the exam will be posted by tomorrow night. Okay. Whew. All right, so let's continue talking. So last time we were talking about limits at infinity. So in particular, there's two things about limits at infinity. Go back to the very beginning of this section. So there's two things that can happen. You can have it where your limit turns out to be infinity, and so that's what happened when we had these vertical asymptotes. You can see that those y values go up to infinity here. So you can have it where the y values go to infinity. But there's also another thing we can do where instead of this limit approaching a number, this limit could be approaching positive or negative infinity. So that would be talking about what happens as the graph leaves the page. So negative infinity being down this way, positive infinity being up this way. Do that. Okay. So you can have the limit as x approaches positive infinity, or the limit as x approaches negative infinity. And a quick kind of graph here. If we're talking as the limit approaches positive infinity, we're talking about the x values as they go off the graph this way. So I could have a function. Sorry, let me mute myself. Joys of dogs. So I'd be talking about like what happens as the graph leaves the page this way. And sometimes what happens is that just the y values just go off to infinity. Or maybe they go down to negative infinity. But other times they level off, right? If you think about horizontal asymptotes, sometimes those y values just level off as the x values go off to positive infinity. And then going to negative infinity, we're talking as the x values go this way. So once again, you might have a graph where who knows what it does. It might level off like that, and the y values might tend towards one y value as you go off to negative infinity. So when you're doing these limits and we're looking at as x goes to positive or negative infinity, you're choosing x values. Normally you choose x values that were close to this number, right? But choosing x values that are close to infinity is, impossible. You'll never get to positive infinity. You'll never get to negative infinity. So you just start choosing big numbers. In fact, I would say 1 and 10 aren't nearly big enough numbers to choose. I would say start with 100 would be a good choice, and then go maybe 1,000. But we'll do it with the way this chart is written now. So we have this function here, and we can plug these x values into this function to see what the y values are. Remember, when you plug in these x values, you're trying to figure out what the y values are of this function. So plugging in 1, right, you have 2 times 1 over the square root of 1 squared plus 2. So 2 over the square root of 3. Plug that into your calculator. You should get 1.54 something. 1.154. Doing the same thing and plugging in 10 to this function right here. right? So 2 times 10 over the square root of 10 squared plus 2. You should get 1.980295086. Do the same thing, but plug in 100. So we're letting those numbers get bigger. That's what we're doing here, is letting these x values get bigger to see what happens to this as we go off this way. We're choosing x values that are really big, x values that are out here. I get 1.999800003. If you get even bigger, if you did like 1,000, right? If you did 1,000, you'd get 1.999998. What's happening to these y values as x gets bigger? It's approaching 2. Yeah. They're getting closer and closer to 2. Go ahead and try it for yourself on this chart over here. Plug in -1, plug in -10, and be really careful when you're plugging it in down here. For instance, with -1, make sure you put parentheses around the -1 when you square it if you're doing this in your calculator. The reason for that is that if you do not put them around the -1, it's going to start giving you errors right here. So make sure that you put parentheses there. Go ahead and do that and tell me what you see it approaching. I'm hearing some answers about approaching -2. So you should be getting, it really should be mirroring itself. -1.154700538. This one should be -1.980295086. This one would be -1.999800003. So this one approaches -2. So what we could say in these cases, over here, the limit as x approaches positive infinity of 2x over the square root of x squared plus 2. As the x values get bigger and bigger, this value goes to 2. And on the other side, the limit as x approaches negative infinity, so these numbers are getting smaller and smaller, essentially. They're getting closer and closer to negative infinity of 2x over the square root of x squared plus 2. This will be -2. Questions on that? Is anyone having any trouble getting these numbers to come out on your calculator? Again, the parentheses are really important here. And if you're using the Casio calculator, maybe I should post, I have a tutorial on how to use this, and I was going to post that tutorial, and I don't think I did. Hold on. Let me make a reminder on my phone real quick. I will post a calculator tutorial for the Casio calculator a little later today. Knowing how to use your Casio calculator or just whatever calculator you're using is really important. So if you're not able to easily get these numbers to come out, maybe take a look a little bit later when I post that tutorial on how to use the Casio calculator, because plugging in stuff on your calculator is very important. And your Casio the Casio calculator in particular will make your life really easy once you know how to use it. All right. So then again, if you do this, if you take a limit and x is approaching positive or negative infinity, and it turns out to be a number, so a number, not infinity or negative infinity or dne, right? If it turns out to be a number, then you have a situation where x is going to infinity and then the function levels off. And as you can see in this picture, and as I mentioned up here, you're looking at a horizontal asymptote. If the y values level off as you get further and further this way, that means there's a horizontal asymptote. Which I will abbreviate as HA because that's faster to write. So this comment here, by definition, a horizontal asymptote describes the end behaviors of a function. So as it goes off the page, you should have talked about end behaviors in Math 126, end behaviors of polynomials. It's the behavior as the graph exits your graphing area. So it's describing just the end behavior. It's not talking about what happens in here. It's talking about what happens as it leaves. And as such, it's okay to cross a horizontal asymptote. So one thing people say is they'll say you can't cross a vertical asymptote, which is true a lot of the time, right? The vertical asymptote. A lot of times you can't cross a vertical asymptote. You just have to make a very specific function. So if I have a function like this and like this, it's not crossing that vertical asymptote, but it's very, very common to cross horizontal asymptotes. So I can have a horizontal asymptote here and have a function that does this. It's okay to cross horizontal asymptotes. You rarely will cross a vertical asymptote, but it's very common to cross a horizontal asymptote. So that's what this is saying here, is it's common to cross a horizontal asymptote. Let me kind of emphasize something on this graph. So there are horizontal asymptotes on this graph. This is the graph of the function that we just were looking at. And you'll notice as the graph goes off, right, positive infinities out here, negative infinities back here, as your x values go to positive infinity, so as it goes off the graph to the right, there's this horizontal asymptote at y equals 2. And that was the limit as x went to positive infinity. And then as x goes to negative infinity, so as it goes off the graph this way, there's a horizontal asymptote at y equals negative 2. So your horizontal asymptotes aren't always going to be the same in either direction. Right? This one has two different horizontal asymptotes. One for going to negative infinity, the other for going to positive infinity. So this shows that in order to find horizontal asymptotes, you have to look at both directions. You have to look at going to positive infinity and negative infinity. So for instance, I'm going to draw a quick graph here. You should remember the graph e to the t or e to the x. That's the graph that looks like this. T squared is the graph, that's just a parabola, right? That looks like this. So we have a piecewise function. When t is less than 0, so the less than 0 part, the function is e to the t. So that's a awful looking function, but it has a horizontal asymptote at y equals 0. When the function is greater than 0, when t is greater than 0, we use t squared as the function. So it's greater than or equal to, so solid dot. And the function looks like this. So if we have this function here, and we do the limit as t approaches negative infinity, negative infinity is clearly less than 0, right? Negative infinity would be off in this direction. And because this graph levels out and has a horizontal asymptote at y equals 0, this limit, right, the limit as t approaches negative infinity, so we're using the e to the t part because we're going to negative infinity, and negative infinity is less than 0. This limit is 0, i.e. there is a horizontal asymptote at y equals 0. On the other hand, if we look at the other direction, and we do the limit as t approaches positive infinity, positive infinity, those x values, those t values are greater than 0, so you're using the t squared part. And if we look here, what happens to those y values as we go off to positive infinity, right? What is happening to those y values? Yeah, I hear it. Positive infinity. Yeah, these y values are going off forever to positive infinity, right? If you plug in, 1,000 to the function, if you put in the t value 1,000, the y value is 1,000 squared, which is going to have 6 zeros. You're going to get 1,000,000. So those are just going to get bigger and bigger. If you're going to positive infinity, that means there's not a horizontal asymptote in that direction. So this function that we have, this whole function here, has one horizontal asymptote, and it has it at y equals 0. Can I answer any questions up through this point? So if you're typing a question, feel free to keep typing. I wish it showed when people are typing, but it doesn't show when people are typing. So I'll kind of go to this next picture over here, this next example. So we have a graph here, and we have some limits to find. I want to point out what's going on here. So there's no arrow, but there's kind of an arrow here. This function, like as it's going this way, it's kind of flattening off. So like you can kind of assume it kind of like flattens as it goes off this way. Just making assumptions. And you can assume that this thing flattens right here. So if we're looking at this graph and we want to find the limit as x approaches positive infinity, so positive infinity is over here, negative infinity is over here, and once again, this is the x value. X value as, the y value of this function as x approaches positive infinity. So we look at what happens as we leave the graph, and it looks like this thing is flattening out, right? It's flattening out to the y value 2. There's a horizontal asymptote, it appears, at y equals 2. So that limit is 2 because it's flattening out, and we can assume that that y value will continue to be 2 as this function continues outward. On the other hand, if we go to negative infinity, the function, it's kind of squiggly and stuff, but it looks like it's flattening out. And looks like it's flattening out around the y value -1. So as my function goes off the screen in the direction of negative infinity, those y values are trending around -1. It looks like it's going to flatten out and stay around -1. What's happening with the limit as x approaches 1? This is kind of a review question. What is the limit as x approaches 1? So 1 is right in here. I hear a DNE. I would agree with the DNE. So here's what's happening. If we look at the left side, so if we do the limit as x approaches 1 from the negative side, so if we do this guy here, of f of x, this is approaching 1. But if we look the other direction as we come from the right side, this is approaching 3. Because these two are not equal, the left and the right hand limits are not equal, it means that the limit as x approaches 1 does not exist. They don't approach the same y value from both directions, so that limit will not exist. Go ahead and do these last two here. Do the limit as x approaches -3 from the negative side, so from the left side, and then from the right side. And what are we getting for approaching -3 from the left, from the negative side? I hear an infinity, right? So -3 right down here. So we're coming from the negative side, so we're tracing that graph. And those y values seem to go up forever. So those y values go to positive infinity. What about from the other direction? From the positive direction, from the right direction. If you come from the right, -1. So here we come from the right, and it looks like, I should probably write this down, -3 from the positive direction, we're approaching -1. Yep, perfect, perfect. So some of this is just kind of review on limits, right? Especially like this guy here and this guy here. But there are a few things we can take away from this. So if you have a limit that equals infinity or negative infinity, you're looking at a vertical asymptote. And I kind of want to summarize this up here. Right? So if a limit equals positive or negative infinity, like in this case right here, this is going to give you a vertical asymptote at this x value. There's going to be a horizontal asymptote if you have a limit as x approaches positive or negative infinity of some function and it equals a number. Not positive infinity, not negative infinity, but it equals an actual number. So if you have a limit and it's going to positive or negative infinity and it equals an actual number, then you have a horizontal asymptote at y equals whatever this number is here. So for instance, with these first two, right, we're going to positive infinity and this equaled a number. So this right here represents a horizontal asymptote at y equals 2 because that's what the number was. This next one here, x approaching negative infinity, also equaled a number. So there's a horizontal asymptote at y equals -1. So maybe I'll write like a quick example right up here. So like if you have it as, I'm just writing a random number here. So for example, if you have, for the vertical asymptote, a limit as x approaches 5 of a function. It could be 5 from the positive side, negative side, or both. It doesn't matter. Put a positive side in there. That would mean, and it equals negative infinity, that would mean there's a vertical asymptote at let me rewrite the at sign, at x equals 5. On the other hand, if you have the limit as x approaches, let's say, positive infinity of a function, and it equals a number, let's say 7, because I like the number 7, then this would mean that you have a horizontal asymptote at y equals 7. Right, so just kind of giving you examples up here. These are not related to this picture here. This is just in general trying to explain how you know if it's a vertical or horizontal asymptote. Can I answer any questions so far? So if you're typing, feel free to continue typing. I have my eye on the chat box. So one thing you learn in Math 126 is that there are tricks for this with some functions. Right. Oh, they changed the notes around. Hold on a sec. I'll come back to that. Okay, he changed the way that these notes are organized around. So this doesn't have rational functions here. That's fine. Right. So preliminary fact number 1. So if you're finding horizontal asymptotes, question. Horizontal asymptote is only when they start to flatten out in the graph. Flatten out as they leave the graph, right? So if it flattens out as it's going off either to the left or to the right or to the left, that would be a horizontal asymptote, correct? But it's not like if it flattened out like this is flat right here, this isn't a horizontal asymptote. It's only when it's leaving the graph. No problem. So preliminary fact number 1, for finding asymptotes analytically. So just not graphing it at all. Like I don't want to graph this function here. How can I find it? By just find these limits by just looking at the function. If you're looking at polynomials, you can eliminate everything except for the highest power, and then you can kind of plug infinity in. So what ends up happening when you're talking about really big numbers? So for instance, if we look down here in this function, I'll finish writing my thing in a second, but if we look down here at this function, if you think about x to the 5th and x to the 4th, when I plug in a number like, let's pick 20, it's going to get really big really fast. Let's pick 12. If I plug in 12 to either of these, so 12 to the 5th is, I'm going to need more room than that. It takes a lot of space to write these. 12 to the 5th is 2, 4, 8, 8, 3, 2. 12 to the 4th is 20,736. So like, look at the difference between these numbers. And that's the number 12. So even if I start multiplying by the number 2,317, this fifth power grows so much quicker than the fourth power that it doesn't matter what happens with a fourth power. Like, the only thing that matters in overall when you're going to infinity or negative infinity is the highest power, because the highest power overpowers everything else to such a dramatic degree. So if I erase stuff here, if I use 24 to the fifth, this is the number 7962624, so 7 million, and 24 to the fourth is 331,776. And that's just 24. Can you imagine if I'm plugging in the number 1,000 here? I can't even plug in 1,000 because it's going to start giving me exponentials in my calculator. This fifth power just grows so much quicker that as we're going to infinity, I don't care about anything that's not the highest power, because the highest power is going to dominate incredibly what happens with a limit as x is going to infinity in a polynomial. So with polynomials, you can eliminate everything but the highest power and then plug infinity in. With polynomials, it's going to come out to be, if you're taking a limit as x goes to positive or negative infinity, you're going to get the answer positive or negative infinity. Let me kind of show you how that looks. So we'll start with this guy right here. So the limit as x goes to positive infinity of p of x. And p of x is this function right here. Because x is going to infinity, that means we can eliminate everything except for the highest powered term. So I don't care about this. I don't care about this. This is the same thing as the limit as x approaches infinity of just x to the fifth. And this is kind of pseudo math here because you really can't do infinity to the fifth. Oh, someone's asking, what does it say after plug? Oops, after plug here. And let me just rewrite it. It's a plus or minus infinity in, depending on whether it's positive or negative infinity that you're looking at. No problem. So if you take infinity, positive infinity, and you raise it to the fifth power, I mean, what are you going to, is this result going to be positive or negative? If you take positive infinity and you raise it to the fifth power, would that result be positive or negative? Positive, right? Positive. So, and then infinity, if you raise infinity to the fifth power, That's just infinity. So this limit comes out to be positive infinity. On the other hand, if we take the limit as x goes to negative infinity of this function, x to the fifth minus 2, 3, 1, 7, x to the fourth minus 1, 2, 4, 0, we can still do the thing where we eliminate everything but the highest power, and that's because x is going to negative infinity. So this is the same thing as the limit as x goes to negative infinity of x to the fifth. And now we can plug in negative infinity. But if you take a negative number, and negative infinity is technically a negative number, if you take a negative number and you raise it to the fifth power, are you going to get a positive or negative number out? Negative. So negative infinity raised to the fifth power should be negative infinity. So I'm going to give you a second just to finish writing. So I'm going to go to the next slide. If you need me to go back, just let me know. So the second fact. In the case where you get well, why don't we just talk about a few things here? If you plug in 1 over a really big number in your calculator, right? You plug in 1 over a really big number in your calculator. You get a really small number. If I make that number bigger, right? You're going to get an even smaller number. So if your denominator gets really big, but the numerator is staying really small, then this essentially becomes 0, right? Like this 0.000, this is a really small number. This is essentially 0. If this number on the bottom keeps getting bigger and bigger, this is going to go to 0. So preliminary fact number 2, 1 over infinity is 0. 1 over negative infinity, I mean, the only thing that would change here, right? I mean, negative, but it's still getting closer and closer to 0. And it doesn't even matter if this is a 1 on top. You could have anything. You could have 5. You could have any number on top. But I'm going to leave it as a 1. Any number on top of infinity, if you're doing limits, is just going to go to 0. So in this case right here, if we look at this limit, the limit as x goes to positive infinity of 3 over x to the 8th. Oops, let's see, there we go. So let's just plug in infinity here to see what happens. So plugging in infinity, we have 3 over infinity to the 8th. That's the same thing as just 3 over infinity. That's this situation here. So this just comes out to be 0. Here's where you have to be a little bit careful on this next one. So we do have the limit as x is going to negative infinity, and we have x to the 1/2 down here. I want you to remember x to the 1/2 is the same thing as the square root of x. Right? It's really important that you remember your exponents and how they relate to radicals. So really, this is the same thing as the limit as x approaches negative infinity of 1 over the square root of x. If I plug in negative infinity, what problem are we going to have here? Yeah, so there's a negative sign. There's a problem in that we have a negative number under a square root. We can't have that. What is that going to do to this limit? What is that negative sign under the square root going to do to this limit? Yep, DNE. Beautiful. Yeah, it can't exist because you can't have a negative under a square root. I mean, any numbers, even like as soon as you're less than 0, nothing is happening here. So certainly as you go to negative infinity, this limit doesn't exist because the graph can't even exist there. However, if you had had the limit as x approaches positive infinity of 1 over x to the 1/2, so the limit as x approaches positive infinity of 1 over the square root of x, this would be 1 over the square root of positive infinity. And the square root of infinity is still infinity. Infinity is a weird number, right? You can take half of infinity and it's still infinity. You can take the square root of infinity and it's still infinity. So this is 1 over infinity, which is 0. So if you had gone to positive infinity instead of negative infinity, the answer would be 0 as opposed to DNE. So let's expand a little further into rational functions. So let's say that you have 2 polynomials, right? This is in their general terms, and I will demath it for you as soon as we get going. Sorry, headset's a little uncomfortable. We have 2 polynomials, and we're taking the limit as x goes to, it doesn't matter, positive or negative infinity. I'm going to put this up here these are subscripts. Hold on, let me write it. So these B sub m's, A sub n, these subscripts on the a's are these are just coefficients. This is just a really mathy way of saying, here's a polynomial. It has coefficients, but the highest term is n on the top, and the highest powered term on the bottom is m. With a polynomial, with a rational function, sort of like with polynomials, on the top and bottom, you can eliminate everything but the highest power. So you can take the limit as x approaches positive or negative infinity and just keep the highest power on the top and the highest power on the bottom. So I'm going to write that in non-mathy terms. With rational functions and limits going to positive or negative infinity, eliminate all but the highest power on top and the highest power on bottom. So it's basically saying you can just ignore all that and just take the highest powered term. So if we look at this first example here, we have the limit as x is going to negative infinity. So because x is going to negative infinity, we can use this rule up here. So I can basically say, I don't need any of that because the highest term is this one on top. On the bottom, negative 3x to the ninth is the highest term. So I have the limit as x approaches negative infinity of 7x to the ninth over negative 13x to the ninth. And you might be saying, okay, well now I can plug infinity in. But wait, you can simplify at this moment. So you eliminated everything but the highest and lowest powers. Now you can simplify. Right? Because these x to the ninths will cancel. So you have the limit as x approaches negative infinity of 7 over negative 13. And the limit of a constant is just the constant itself. So your answer here is negative 7 over 13. Why negative 7? So like, oh, I just took this negative sign that was down here and I just moved it up top. So this negative is just the negative that was down there. So 7 over negative 13 is the same thing as negative 7 over positive 13. Yeah, no, it's okay, which is the same as negative 7 over 13. Either of those are fine. I just typically don't like to put the negatives in the denominator. Right? Looking at this next one, same idea. We are going to positive infinity. So the highest powered term on the top is the 14y. On the bottom, the highest powered term is negative y to the fourth. So we have the limit as y approaches infinity of 14y over negative y to the fourth. This can be simplified. Right? So if you have y over y to the fourth, this is, I know I have numbers here, but this would be 1 over y to the third. So it's heavier on the bottom, so the exponent ends up staying on the bottom. So when we simplify this guy, this is 14 over negative y cubed. Make sure, if you're feeling uncomfortable with that math, you definitely want to review your exponent rules. But essentially, here's what's going on. Y to the fourth is the same thing as y times y times y times y. One of these y's cancels. Now you have 14 over negative y times y times y, which is 14 over negative y cubed. So if this is confusing to you, definitely make sure you review quotients of exponents. So now this is as simplified as it can get over here. So I can plug in negative infinity. So I have 14 over negative infinity cubed. I'm going to start just with this negative infinity cubed part. You might see where this is kind of going already, but I'm going to start just with this part here. If you take negative infinity and you cube it, it's going to remain negative and also infinity. So now we would have 14 over negative infinity, because this negative sign is still out here. A negative and a negative, that's just going to make positive infinity. So we have 14 over infinity, and we already talked about those coming out to be 0. Now, you could have seen that happening right here. We could have seen, it doesn't matter if it's negative or positive on the bottom. It wouldn't have mattered if we had 14 over negative infinity. Either way, it would have come out to be 0. But regardless, it's good to practice. Oh, it is approaching positive infinity. Good call. Y2, so somebody said Y2 negatives. I thought it was approaching positive infinity. Because I'm blind and I can't read my own handwriting. Ignore all those things. No, I totally plugged in this. That was how it was all along. Good call. I appreciate that. So now you're going to have 14 over infinity cubed is going to be infinity. So this on the bottom will be negative infinity. And the result, once again, won't change. But very good to point that out because it does change in other situations. So 14 over negative infinity, then 0. I appreciate you pointing that out. Right, other questions so far? So I'll move, if you need me to move back, just let me know. So I want you guys to try these two examples out. Okay. Try these two examples. Let me know when you're ready. I'm going to go ahead and mute my mic. I'll go ahead and, I don't need to really pause this. It won't take you too long to do it. I'm going to mute my mic, go ahead and do this one. And when you have answers, go ahead and put them in the chat box for A and B on 1.4.15. Seeing an answer, I'm seeing a positive infinity. I'm assuming that one is for the first one. So let's work through that first one. We do have z going to negative infinity, and this is a rational function, so we can just eliminate all but the highest power on top and the highest power on the bottom. So you have the limit as z goes to negative infinity of 2z to the 6th over 9z to the 4th. We can simplify here. So we have the limit as z goes to negative infinity over, this will become 2/9 z squared, right? Z to the 6th over z to the 4th is z squared. Plugging in negative infinity here. If you square negative infinity, it'll be positive infinity. So you have 2/9 times positive infinity. And once again, if you multiply infinity by a number, like the most you can do is you can change the sign. So if this were like a negative 2/9, you could make it negative infinity, but 2/9 times infinity, that's just going to be infinity still. You can take infinity and subtract 10,000 and still have infinity. You can take infinity and add 1 to it, and it's still infinity. You can take 10 times infinity, and it's infinity. The only thing weird you could do is like if you do negative 9 times infinity, this would be negative infinity. But this one does come out to be positive infinity. Same idea down here. We're going to positive infinity, so we can look at just the highest term on the top and the highest term on the bottom. So the limit as x approaches infinity of 7x to the 19th over negative 3x to the 100. Simplifying that, we would have 7 over negative 3x to the 81. Oops. Now I can plug in. I don't need to write limit anymore. So now I have 7 over negative 3 times infinity raised to the 81, which even though that's a crazy big number, still just the same thing as negative 3 times infinity, which would be negative infinity on the bottom, which would give me 0. So 7 over negative infinity would give me 0. Can I answer questions on either of those examples? So question is, when it's negative infinity, do you always get 0? Yep. So if it's 7 over positive infinity, 0. If it's 7 over negative infinity, 0. If it's negative 7 over infinity, 0. I mean, you could look at it as being negative 0, but negative 0 would just be 0. So yeah, regardless of the type of infinity, if it's a number over infinity, positive or negative, it'll come out to be 0. Can I answer any other questions? So then kind of going back to this idea of horizontal asymptotes. To find the horizontal asymptotes, you're going to take the limit in both the positive infinity direction and the negative infinity direction. So you take the limit as x approaches positive infinity of the function and the limit as x approaches negative infinity of the function. If they equal a number, then you have a horizontal asymptote. If they equal positive or negative infinity, there's none. So if it equals a number, then there's a horizontal asymptote at y equals that number. If they equal positive or negative infinity, no horizontal asymptote. So for instance, if we're finding the horizontal asymptotes of x squared over x to the fourth plus 1, we'll take the limit as x approaches positive infinity of x squared over x to the fourth plus 1. And because we're approaching positive infinity, or an infinity in general, we can take the highest term on top and the highest term on bottom. I want to remind you, right, that you can only do this. You can only do this when you're approaching positive or negative infinity. It does not work if you are approaching a number, right? So if this right here is a number, you don't do this. You cannot use this rule. This rule only works with infinities. And I'm telling you this because at least one of you on the test is going to end up trying this, and you're going to get the question completely wrong. So remember, it's only with the infinities when x is approaching positive or negative infinity that you can just take the highest on top and bottom. So the limit as x approaches infinity of x squared over x to the fourth. Simplifying that, we have 1 over x squared. So 1 over infinity, which is 0. I mean, it'll be infinity squared, but infinity squared is just infinity, so 0. Because we got an actual number here when we did this, we can right away say there's a horizontal asymptote at y equals 0. There might be another one, so we have to take the other direction, but we can say at least that there's one at y equals 0. So we'll go to negative infinity, and the problem is going to play out really similar, right? So the steps look the same. You get x squared over x to the fourth. Oops, there's a negative in there. The limit as x approaches negative infinity of 1 over x squared. So 1 over negative infinity squared, 1 over infinity, which is 0, which is the one we already had. So we can say that there is a horizontal asymptote at y equals 0. Here's a trick. And this trick is only with rational functions. So this might not work if you have like a square root involved. So it has to be a polynomial over a polynomial. If there's a square root involved, if there's an absolute value involved, this trick won't work. But if you have a polynomial over a polynomial, the limits in the positive infinity and negative infinity directions will always end up being the same. So this right here is a rational function because you have a polynomial on top, a polynomial on bottom, polynomial on top, polynomial on bottom, polynomial on top, polynomial on bottom. So these three are all rational functions. So when I'm doing this, I can make my work a little bit quicker. I still need to show the work, so I'm doing as x goes to infinity of 5x cubed minus 900, 10x cubed minus 3x squared plus 7. So because I'm going to infinity, I can take the highest power on top and the highest power on bottom. So I have 5x cubed over 10x cubed. I can simplify that. So the x cubes will cancel. And then I have 5 over 10, and that's just a constant. So the limit of a constant is the constant itself. 5 over 10 simplifies to 1/2. So as a horizontal asymptote at y equals 1/2, I know that's going to be the only one because that's a rational function. But to show the other side, I'm just going to say, right, I can write this out. You can just write the steps, like you know it's going to turn out the same, so you don't really have to think while you're doing this. 5x cubed over 10x cubed. You know this is going to equal 1/2. So you can just kind of truncate that work a little bit. Still showing the important steps, so showing the step where you eliminated, but then going kind of straight here. So one more. Look at as the limit as x goes to infinity of x cubed plus 7x plus 1 over x squared minus 3x plus 2. As x is going to infinity means with a rational function, we can take the highest power on the top and the highest power on the bottom. So we have x cubed over x squared, which simplifies down to just x. So if you plug infinity in for x, you get infinity. If you get infinity, remember right back up here, if you get infinity, there's no horizontal asymptote. So this question, remember, was asking about horizontal asymptotes. So there's no horizontal asymptote there. And then for the other direction, I guess I should add, they'll be the same, except I guess maybe the better thing to say here, the horizontal asymptotes will be the same. It's not necessarily the limits, because the limits in this one are going to turn out different. It's just that they're going to have the same horizontal asymptote, which is none. So important correction there. Make sure you correct that. The horizontal asymptotes will be the same. But if we look down here as we do the limit as x approaches negative infinity, if we plug in negative infinity to x, you're going to get negative infinity. Either way, it results in the same result of no horizontal asymptote, but these limits are different. So that's why that correction needs to be there. Questions on any of those horizontal asymptote problems? So let's talk about some tricky cases. So some situations where you're going to positive or negative infinity aren't rational functions. These are not rational functions. These are just other types of functions. Here's something really important that we've kind of mentioned, but not really. But this fact will come important right now. If you're taking the square root of x squared, this is not x, it's the absolute value of x. And the absolute value of x is technically a piecewise defined function, which is x if x is greater than or equal to 0, and it's negative x if x is less than 0. And to kind of explain why this makes sense, think about the absolute value of negative 2. Would we all agree that the absolute value of negative 2 is positive 2? Just without looking at this chart over here, yeah. So like, we know this is true. Now, if we use this function here, right? So if we use this, it would say that if we have the negative 2, all right, so here in this case, x is equal to negative 2. So we'd be using this bottom portion. So this means it would be negative negative 2, which makes it positive 2. So that's how that function works, is essentially it says, okay, if you're negative, then just put another negative sign in front. And if you put a negative sign in front, you'll just cancel out the negative sign. So technically, absolute value functions are piecewise defined functions. And we can use that down here. So we can still do the trick where we eliminate everything but the highest power in the numerator and denominator. Numerator slash denominator. So I have this 2x, I have this x squared. So what I'm doing, I am going to still go to positive infinity. I have a 2x on top. The square root on the bottom needs to stay. So I have the square root of x squared, which is this thing up here. So technically, this is the limit as x goes to infinity of 2x over the absolute value of x, right? Because we just said the square root of x squared is the absolute value of x. Now, we can't directly cancel these as it looks. We have to determine whether we're using the top piece or the bottom piece when we look at this absolute value of x. Right? Absolute value of x is equal to x if x is greater than or equal to 0, and negative x if x is less than 0. So if x is going to positive infinity, am I using the top piece or the bottom piece of this piecewise function? Am I using this one or this one? If x goes to positive infinity, is positive infinity greater than or less than 0? Top piece, yes. Beautiful. we would use the top piece, which is just x. So in this case, because x is going to positive infinity, I can say that the absolute value of x is just x. And now those x's cancel. So we have the limit as x goes to infinity of 2, which the limit of a constant is just the constant itself. Now, on the other hand, if we look at this bottom example, same function, but we're going to negative infinity instead, our process will look similar, right? We're going to an infinity, so we can keep the highest power on top and the highest power on bottom. So we have the limit as x goes to negative infinity of 2x over the square root of x squared. Once again, we will replace the square root of x squared with the absolute value of x. But now, right, absolute value of x if x is going to negative infinity, are we using the top or bottom piece? Using that bottom piece, right? The bottom piece, because x is less than 0, right? Negative infinity is less than 0. So you're using the bottom piece. So instead of the absolute value of x, I'm going to use this negative x piece. And now, when things cancel, it looks a little bit different because there's a negative down here. So 2x over negative x, that simplifies to negative 2. And the limit of a constant is the constant itself. So this is the function we were looking at back at the very beginning here. So questions on that one? What if the exponent on the bottom is greater than 2? That's a good question. So this gets a little complicated. And we will do one, I think they kept that one in here. Yeah, we will do one that's like that. But like, what if you had like the square root of x cubed? Something like this. With this guy here, you have less of a problem. So there's not as big of a problem because if you plug in negative infinity, you just end up with like a negative on the inside of a square root, so it doesn't work out. But if you have the square root of x to the 4th, this is where the conversation gets a little bit more weird. So technically, the square root of x to the 4th is the absolute value of x squared. However, x squared is always positive. So taking the absolute value of a number that's always positive ends up being just x squared. But then so you're not going to have to get this deep into it. And I'll show you on the next page how it kind of works out. But if you have the square root of x to the 6th, by the way, if you took me for Math 96, which I don't know if anybody's followed me from Math 96, but if you took me for Math 96, I just completely omitted talking about this because it's like this part here is all very confusing. So if you have x to the sixth, the square root of x to the sixth, this is the absolute value of x cubed, which then is equal to x cubed if x is greater than or equal to 0, and negative x cubed if x is less than 0. So the conversation gets really confusing because it all depends on if you end up with an even exponent or an odd exponent at the end. And if you end up with an odd exponent at the end, then it separates into a piecewise function. And if you end up with an even exponent at the end, then it doesn't separate into a piecewise function. I'm not concerned about you knowing this. We're going to do one where it's like you're going to basically, the things you would have to worry about is this situation here, and then I'll show you another one on the next page. But basically, as long as you know that the absolute value of x is equal to x if x is greater than or equal to 0, and negative x if x is less than 0, that's the thing that I want you to know. This right here is just bonus information. Yeah, no problem. Sorry, I wish it was a nicer answer. It's just unfortunately not a nicer answer. All right, so let's look at this limit here. So we're going to positive infinity. So we're going to take the highest power on top and the highest power on bottom. Now we are going to leave his radical with him on the top, just like we did before. So this is the limit as z approaches infinity. And I know it might be kind of blurry on there, but if you have the notes printed off, you should be able to see it. It's the fourth root of z to the ninth over z squared. You need to be able to simplify this. So something you should remember from Math 96. If you have the mth root of z to the n, the exponential form of this is z raised to the n over m. So for instance, if you have the third root of z to the fifth, this is z raised to the 5/3. So I'm going to take the limit as z approaches infinity, and I'm going to change this top one to z to the 9/4 over z squared. To simplify, once again, another exponent rule, which we've kind of already used, but if you have z to the m over z to the n, this is equal to z to the m minus n. So we have the limit as z approaches infinity of z to the 9/4 minus 2. So numerator exponent minus the denominator's exponent. We have the limit as z approaches infinity. If you do 9/4 minus 2, you're going to get 1/4. And z to the 1/4 is the same thing as the fourth root of z. So you're kind of doing the backwards version of this. So this would be a 1, and the m would be a 4. Plugging in infinity, you have the fourth root of infinity. And the fourth root of infinity is just infinity. If you did this same problem again as z goes to negative infinity, your steps would be the same, right? You do this step, you do this step, you do this step, you do this step. Would we all agree that those steps would all remain the same? The only difference would be the very end part if you're doing negative infinity. So you'd still get down to limit as z approaches negative infinity of the fourth root of z, taking that from up there. You have to change it back to a radical, sort of, kinda. The problem is that, like, if you do infinity to the 1/4, this will come out to be a infinity. But if you do negative infinity to the 1/4, you have a problem. So, like, what you're going to see down here is that I'm trying to take the fourth root of negative infinity, but I can't take an even root of a, let me move this here. I can't take an even root of a negative number. So this one ends up not existing. So making it into a radical helps you easily identify that. If you can see it from this view, you can leave it here. But a lot of times it makes it easier for your brain to just kind of not be concerned about it. If that makes any sense. Yeah, no problem. No problem. Let's use purple. So as a note, just be careful when even roots are involved because you can't take an even root of a negative number. We cannot take an even root of a negative number. So we do have like 7 minutes left. Clearly, I'm not going to get to 1.5, so we're just going to have to use Wednesday to talk about 1.5. I might set up an additional time to do a review, and I can just kind of post that video later. So we'll talk more about that on Thursday, but I might set up a time on Friday, or not Thursday, Wednesday. We'll talk about that on Wednesday. So I might set up a time on either Thursday or Friday where I hold a class session, quote unquote, where I do the stuff I would have done on the review on Wednesday that we're not going to have time to do on Wednesday, and record it and post it so that you have that review session as well. So we'll talk more about that on Wednesday, though. We are almost done with this section. Yeah, we are almost done here. So just a few more problems. So let's look at this one here. We have the limit as x approaches infinity, and we have some kind of like a mess going on here. So if you did this, I mean, so you're going to get like 2 times infinity minus the square root of 4 times infinity squared plus 1. This is going to come out to be infinity minus infinity. And remember, when you get infinity minus infinity, you need to use a trick. Can't be done. Use a trick. In this case, if you have radicals involved, multiplying by the conjugate tends to be a good idea. So I can take this and multiply by 2 plus the square root of 4x squared plus 1. Now I can't just do that without consequence. I have to do that on top and bottom. So now we have a difference of squares. So we have the limit as x approaches infinity. And then, oops, this should be, my bad here, this should be a 2x. So you get 2x times 2x, that'll give you 4x squared. The middle terms will cancel, and then the square roots will cancel, so you'll be just subtracting 4x squared plus 1. On the bottom, you'll have 2x plus the square root of 4x squared plus 1. If we simplify, right, so 4x squared distribute the negative, minus 4x squared minus 1 over 2x plus the square root of 4x squared plus 1. The limit as x goes to infinity. The 4x squareds cancel, you get a negative 1 on top, and then 2x plus the square root of 4x squared plus 1. What we're going to notice here, so like if we try to, dealing with the highest power on top and bottom is kind of weird because you have an x squared under a square root, which is kind of like an x, so these are kind of the same power. So what we're going to do, since there's nothing to do on the top here, we're just going to go ahead and plug in negative 1 over 2 times infinity plus 4 times infinity squared plus 1. If we plug this in, right, you're going to end up with infinity plus another infinity. So you end up with negative 1 over infinity. So you end up with 0. Now, just so we know, remember, negative infinity minus negative infinity does not always equal 0. And I want to point that out. In this case, it turned out that it did. But it does not always. Now, if we do the same thing, so let's not even think about the trick here. Right? We started here by trying plugging in, right? But we got infinity minus infinity, and then we did a trick. But if we start this one and we're going to negative infinity instead, right? Negative infinity. Let's just try plugging in the negative infinities. So you have 2 times negative infinity minus the square root of 4 times negative infinity squared plus 1. So 2 times negative infinity is negative infinity minus 4 times negative infinity squared is positive infinity plus 1. So there's a question, if the infinities cancel, then wouldn't they equal 0? Not always. So not all infinities are created equally. So some infinities are bigger than other infinities. And I think we did an example of that. Here. So we ended up with this one right here, way back. You got infinity minus infinity. This was a different situation. We were going to 0, but you end up with infinity minus infinity, but the answer was infinity. So infinity minus infinity could be infinity. Or it could be 0. It could be a number of things. But the problem is that infinities grow at different speeds. So if one infinity grows faster than another infinity, even though they're both infinity, they don't cancel. So they're not like regular numbers. Like if we say x minus x, that'll always be 0. But infinities have special properties that make it so that not all infinities are the same infinity. No problem. So if I come back to this guy here, we now have negative infinity minus everything on the inside of this is just like the square root of infinity. So now we have negative infinity minus infinity. And if you have infinity minus infinity, if you have negative infinity minus infinity, That just equals negative infinity. So I kind of wrote this on the other one. If you have infinity minus infinity, this is a problem. If you have negative infinity plus infinity where they cancel, this is a problem. In either of these cases, you would need to use a trick. But if you have infinity plus infinity, this is infinity. And if you have negative infinity minus infinity, this is negative infinity. So the only case where we have to really worry about using a trick is if the infinities were to cancel. If the infinities just kind of stack on each other, then you can just say, oh, okay, well, infinity plus infinity, that's infinity. Negative infinity minus another infinity, that's just negative infinity. So that's that. So what I will do, I need to update the homework. So I'll do that very soon. I will update homework 3, and then I will update the due dates on everything so that they are due on Mondays. And then on Wednesday, we will talk about section 1.5, and we will also talk about, I'll set up another time where I do a review session so that we can go over all the stuff that we've talked about in Unit 1. And then I will post a review, hopefully before tomorrow night. So that'll be ready for you to look at. I think that's all the things I need to say. Do I have any questions before you get going? If not, I hope you have a fantastic Monday. Thank you guys for being here. I appreciate you guys. Have a good day. I'll see you later. Bye, everybody.